So let's talk about this required practical investigating energy transfers. Now you'll be glad to know that compared to this specific heat capacity practical, this one is a doddle. Essentially what you do is you get a glass container. Most commonly I've seen this done with a beaker of some size. You have two insulating materials. Here I have bubble wrap and newspaper. And you're going to see which of the two is the best at preventing thermal energy transfer from the inside of the beaker to the outside environment. Basically, which one's going to keep the heat in. And then all you need to do is boil up a kettle and measure the temperature change over time with a thermometer. I mean, there are some subtleties to this, I will grant you. Number one, for example, with the water, that's a control variable, the amount of water. So it needs to be the same every go. So when you do it with your bubble wrap or your newspaper, it needs to be the same amount of water. How do you keep that under control? I've seen it done in two ways. One, volume, so the actual physical space of the water, which you would use a measuring cylinder to measure that volume, or mass perhaps, so you've got the same mass of water each go, and you're going to want to use a balance for that. It doesn't matter which method you use as long as it is the same each time. Okay, what else needs to be taken into consideration? Well, you are going to need to do a control. So what I mean by that is an experiment with no insulation. With no insulation. Now, why would you want to do that? Well, if you come back and say, oh, brilliant, I've done my bubble wrap experiment, and over 10 minutes it dropped by 77 degrees C, and I did my newspaper, and that dropped by 88 degrees C. Well, that's brilliant, but how much does it drop with no insulation? You don't know how much the bubble wraps affect it, and you don't know how much the newspapers affected it if you don't have a control result to compare yourself against. What other considerations do you need? Well, there's the old thing about insulation. Insulation on top. Oh, what do I mean by that? Well, here's your beaker, and yeah, okay, you've secured your bubble wrap and your newspaper or whatever it is all the way around the sides. Brilliant. It's been taped or rubber banded or whatever in place, and then you've got your thermometer sticking in the top. Excellent, brilliant, measuring the temperature at all times. Excellent, well done. But you've got a huge gap here at the top, and heat can escape. And if you remember, that is convection, where hot air rises. You can't really tell how good something is as an insulator if you're hemorrhaging heat energy out of the top. So you need to make sure that you have that covered over. You need to make sure that time is controlled as well. That's also a control variable. And you're going to want a timer for that, and you're going to want to take regular readings. I don't know, every 30 seconds, every minute, something like that, for a defined amount of time. So let's say every 30 seconds up until 5 minutes, something along those lines. Okay. You'll then have some data, and you can start plotting it in a graph, like so, with time along the x-axis and temperature up the y, and it will look something like this. Your temperature will start off really high, and then it will go like that. Okay, and that could be material A, and then you do it again with a different material, and maybe its line looks more like that, and that would be material B. And you could tell straight away that material B is the better insulator, because that temperature for material B, if you look at the line, the gradient is less. It's a shallower line, which means it's cooling down more slowly. It means it has lower thermal conductivity. I can spell today. Lower thermal conductivity than material A. You see? Not that I want to spoil the end of the experiment for you, but basically what you will find is that materials that trap air are the best insulators. Well, why is that? Well, if you remember what gases look like, gases are spread out little particles all over the place. And if you trap these in a particular place, like let's try that again, let's switch that up. If you trap them in a particular place, well, first of all, you have stopped them from doing convection, because you've trapped them inside, I don't know, a bubble in bubble wrap, and also energy moving when these particles collide. So if that one collides with that one, so passing along energy that way is going to be really, really slow. So you are minimizing energy loss that way. So anything that traps air is a good insulator. Like if you think about wintertime, when you get cold, what do you put on? You put on gloves, you put on a hat, you put on a woolly scarf, you put on a jumper. These are all things that trap tiny pockets of air, because air is the best insulator, or gases rather are the best insulators. So if you were going to carry on this experiment, what else could you do? How could you extend it? Well, you've compared bubble wrap and newspaper to see which is the best insulator. So there's the old chestnut of more materials, a wider range, but also thickness. So how does thickness of the material play out? So if you had one layer of bubble wrap versus 2 layers of bubble wrap, which would be the best insulator? Well, hopefully you already know, don't you? It's going to be the 2 layers of bubble wrap, because thicker materials insulate better. Basically, this is just longer for the heat to travel out. But as experiments go, this one is nice and straightforward. Thanks.